Howdy, everybody. My name is Arthur Dohler, and I'm here today to talk to you about bias in AI. For starters, let's kick this off by playing a game. I want you to grab your phone, take it and just pull it out of your pocket. I know you're not usually supposed to do that at conferences when you're listening to talks, but we're going to do this together. Go ahead and open up your messaging app, whichever one you happen to use, and if it has predictive text enabled on the keyboard, and go ahead and type in this sentence: "You're unintelligent," and then see what your app suggests for the next words. I'll give you a couple seconds to do that. Typically, if your phone works like mine, you're going to see the word man suggested and possibly guy. What you won't see are girl, woman, etc. Let's try another one. Go ahead and try this statement: "You're acute." Again, if your phone works like mine, the word girl shows up. Nothing for guy, boy, etc. Now, this seems like a little bit of a, spurious example. Why does this actually matter, what your predictive text says on your keyboard? Well, this is really a symptom of a larger problem. AI and machine learning use is drastically on the increase in our industry and software in general, and it's becoming easier to do. At the same time, it's becoming more powerful. We're able to process more data, do more things with it. And we're using it to solve complex and important problems. And we're using it to supplement the workforce, especially in remote times when we don't necessarily have access to the staff we need for all of these things. Because of those two things, we can't always verify the output manually from these algorithms, from this AI. Above and beyond that, we don't even know how this works sometimes. We're relying on something like TensorFlow, where the underlying logic, we may have a rough model of it, but we don't necessarily know how it works. Worst case, we're buying some kind of prepackaged black box AI off the shelf product, and we have no idea what's going on because it's a proprietary secret. Lastly, regular developers are writing these things. It doesn't take a cadre of research scientists in a university to build a model. It doesn't take them 3 years to go build a model anymore. You can do this in an afternoon. You can find a TensorFlow document, like tutorial, and have your first TensorFlow models built 15 minutes, 30 minutes. And these things have real consequences when you start putting them into practice, when you start putting them into the real world. And you have to be right the first time. Here's an example of a consequence. There are places in the United States that use what's called risk assessment software for evaluating whether people who've been charged with crimes should be out on bail, should be released on bail. These assessment pieces of software rated people from 1 to 10. This chart shows the number of people rated in that category. The top score are for white people. The bottom chart is for black people. Or no, other way around. Sorry, black people is the top one, white's the bottom one. Look, if you don't see a problem there, then we have to have a talk. But this should be fairly obvious why this is a problem. Later, this algorithm was analyzed, and it was found to be no better than a coin flip as far as whether it actually predicted recidivism, as far as whether it actually predicted any risk from this individual. The judge may as well have flipped a coin. Here's a second example. Natural language processing was a big thing a couple years ago. It's died down a little bit now, but we're still doing a lot of it. Here's an example of natural language processing that had some consequences. This is sentiment analysis of sentences involving common names of various ethnic types. Now, sentiment analysis, if you're not familiar, is a process by which you basically rate, does someone view this, or is this statement positive or is it negative? Do they have a positive sentiment or a negative sentiment? If they say this thing sucks, that's negative. If they say it rocks, that's a positive. If you included common ethnic names in the sentences, you started seeing disparities as far as how those things were rated. Positive, in this case, positive is higher, a positive number, and a negative is a negative sentiment. So sentences involving common black first names had a more negative sentiment. That's kind of ridiculous. Now, today when I'm talking about this, I don't want to talk about fault, and I don't want to talk about blame. I want to talk about the reality of the situation and the responsibility that we have as developers to deal with it. All data sets are biased, and all algorithms are biased. It's kind of the point of an algorithm. If it's not biased in some way, it's not helping you make a decision. An algorithm that turns around and just shrugs at you isn't going to really be helpful. So today, we're going to talk about a couple different types of problem with AI and machine learning. 6, 7 if you count weird, but we're going to talk through these things. Now, I kind of like to think about these as ghosts in the machine learning. And I know what we do with ghosts because I've had a little bit of experience in that category. What do you do with ghosts? We bust ghosts. So today I'm going to talk about 7 of these individual things and how you can start addressing them if you're working with AI and machine learning. So, well, before I get into that, let me state, this is not going to get very deep into the weeds of the individual algorithms. This isn't going to be heavy on math. In fact, there's very little math, almost no math at all. We're going to talk about broader things that you can do to deal with these problems. So with that said, let's get right into it. First class that we're going to deal with is phantoms of false correlation. The phantoms of false correlation show up when you have a data set and you're not sure what to do with it. Your boss says, oh, here's the data we've collected from this for the last 7 years. Go see what you can find in it. In this case, you're really just going fishing. You're just digging into the data and you're going to try and find something. When you do that, you're going to find something. It just may not be something useful or valuable. You're going to find arbitrary correlations. And this can get us really confused about what things actually predict other things and what things just correlate with other things. To do that, we have to explain that. We have to talk a little bit about correlation. Correlation is a term that describes how closely two data sets fit, two data series, how close do they correlate with each other? Are they right on top of each other? Do they kind of go along with each other? Humans can do this pretty well visually, but there are mathematics ways to do it because obviously a machine learning tool is not going to do it visually. But you can find false correlations if you just go in and wander into your data, not understanding what it is you're looking for. For instance, the number of people who drown by falling into a pool does correlate with the number of films Nicolas Cage has appeared in, but the two are not causative. As funny as it might be that that was true. Similarly, the divorce rate in Maine, the US state of Maine, has nothing to do with the US per capita consumption of margarine, but they're correlated with each other. And lastly, the letter in the winning word of the Scripps US National Spelling Bee has nothing to do with the number of people killed by venomous spiders in the world. But again, they're correlated with each other, although that would be pretty funny if it were. These false correlations can lead you to believe things about your data, lead you to believe causative things about your data that aren't true. So what can you do about it? Well, the easiest way to avoid these is really to know what question you're asking up front. Don't just go in and look for things that correlate with each other and say, hey, oh, these two things kind of look the same. One must be causing the other because I can come up with a narrative that says that's true. Sit down and ask yourself, I want to figure out what things cause this to be higher. That gets you off to a good start. Secondly, you can actually try using conditional probability over correlation. Now, conditional probability is a tool that allows you to say these things are actually conditional upon each other using probability. This is the only math I'm going to have in here. Don't worry. It's computing the likelihood of one event given that another event has already occurred. Probability, folks. So class 1's fairly easy to deal with. Class 2 gets a little thornier. That's the specter of biased sample data. All right. Maybe you don't know what the difference is between data and, say, sample data. Well, let's talk about an example where you're analyzing and building a machine learning tool around mortgage lending. Now, historically, especially in the US, mortgage lending can be problematic. And it's a lot of data. How long have we been, selling houses? You can't necessarily feed all of that data through into your machine learning algorithm to build a model. And there are reasons you don't want to. But what you do then is you assemble a sample set, a set of data that you're going to train your thing on. Well, you take the sample set and split it into 3 parts. One you will train your model on, one you'll test your model on, and one you'll do for validation. Not really going to get into the interplay of how you deal with these things. There are lots of other resources online that will teach you how to do this. But once you have a sample set, you're looking effectively to pick one thing that is the dependent column. That's what you're trying to predict. And the rest of these things are independent columns, independent variables. And those can be predictors, but they aren't always. So let's say you have your sample data. You've taken your big set of data and you've broken it down into sample data. And now you're trying to look for what things predict other things. Well, it might be problematic for various reasons if you picked one of these columns, one of these variables, as an independent variable. If you said, well, okay, let's just build my models and assume that race affects the outcome so that the machine learning thing can look at the race and say, oh, well, that person is white, so they get the thing, they get the mortgage. Obviously, that can be problematic, if not outright illegal. But those data points are in your data set, especially if you're looking at, say, US historical mortgages. Redlining was a huge thing, and arguably still is, where certain people are priced out of markets or prevented from getting mortgages in certain markets because of their race. Women couldn't own property in the US until shockingly recently. And so that's going to also affect your data set. The outputs of machine learning on biased data sets are biased because of the way that these things work. AI and machine learning is nothing more than math. Your data is shaped then by the system that created it. It's an artifact of that system. The data from historical mortgage records in the United States is shaped by the system that was giving people mortgages. It's not like that data came into being just by itself. This affects both what variables exist as well as its outputs. So for instance, going back to the historical mortgage data, you're not going to see, for instance, any other genders than male and female in that mortgage data, right? And not until very recently. The existence of transgender people was, erased in that data. You can't burrow into it. You can't find out if it's there. It's important to talk about bias in your data set because unless you are sampling data from some kind of remarkably natural source like weather or whatever, your data is biased. Guaranteed. Because data that we have is based on decisions that humans have made in the past. And humans make a ton of really bad, really wrong decisions. Okay? Humans do stupid stuff all the time. And when we do those stupid things in this modern computerized economy and environment and world, those choices get baked into amber. They're preserved for all time as a row in a database and calcified. And we look at that and we say, well, this is what the data is. This is what it should be, right? This is historic. This is history. Because that's what we call a bunch of human decisions. We don't call it data. We call it history. History is not always accurate, right? Just because you've recorded something doesn't mean that it's inviolate. And it doesn't mean that it was recorded correctly or that the choice that led to, even if it is recorded correctly, it doesn't mean that the choice that led to that data entry point was good or something to be replicated. Because that's the real secret of machine learning, is that all it really does is take the past and make the future kind of look like that. And a bunch of companies have spent a lot of time and money trying to make this work. Amazon spent an immense amount of time and energy trying to build an AI recruiting tool, and they literally could not get it to not be biased against women. This is Amazon. They have more money than I will ever have, and certainly more hours of developer time. And certainly they have a lot of people there that are smarter than me for sure. And they couldn't do it. The chances that one individual developer is going to be able to handle this is slim. And that has effects. That can show up in the world. This is a tweet that I was given permission to scrape from a grammar assisting tool that, much like the examples we did at the very beginning, showed a suggestion for grammar. And this grammar tool was saying that there's an unusual word pair here, that the noun girl isn't usually combined with the adjective successful. Maybe you should use lucky or happy. Those things propagate biases back into the world. It takes biases that exist in your data and it puts them back out again. Now, there can be a couple reasons for bias besides the data itself being biased. Your sample might not be representative. If you've constructed your sample poorly, it may not have all of the things in it that the machine learning tool needs. So constructing your sample correctly is also very, very important. But the data itself might not be representative. Again, women could not, in the US, could not get a mortgage by themselves until relatively recently. There's data, if you're pulling data from like the 1950s in the United States, you're not going to see women getting mortgages. So that data set is not representative at that period in time. And you might ask, do you have all of your user types? Maybe you're doing a beta, you're releasing things into the wild, doing some kind of initial test, and you're getting data back. You've pulled in a bunch of early adopters. Is that all of the users that you're going to have? Are those all the types of users that you're going to have for your software? Building a piece of tooling or a machine learning machine learning model off of nothing but the beta users that you have can lead to some significant problems down the road because you don't have a representative data set. So what can you do about this? Well, the first thing is to remember that models represent what was. They don't tell you what should be. All machine learning is going to do is take something from the past and make the future look like that past. That's what they do. So you need to be aware that you're making choices when you implement a model, when you build a model, and when you put it into production. You can try finding a better data set. Maybe introduce it from different countries, different cultures. There are other sites that have a bunch of data sets out there that have worked to scrub bias from them. Those are great places to start, especially for things like language processing. Those are things that really have gone along, people have gone a long way to try and scrub bias out of those things. You can also build a better data set. Assume, hey, I know that we're where I want to be now in terms of egalitarianism. We're only going to work with modern data for modern mortgages. You can make an argument about whether that's true or not, but you can build a better data set. You can also turn around and explicitly just prevent your model from even looking at these columns like race or gender. That's actually fairly easy in most machine learning tools. Just say don't even pass it in as part of the data when you're training it, right? Or you can apply different weighting depending. But you have to beware of shadow columns because things like race and gender in the United States, well, race especially, is heavily correlated with postal codes. So if you include postal code, what can happen is your machine learning algorithm will pick up that people from these postal codes should not get mortgages, which is a shadow column for race. So you have to watch for those things happening in your data as well. You can make sure that your sample set is representative. And I included a couple of resources here at the bottom of the slide. The slides will be posted at the link at the very beginning, and there's a link at the end too for where you can grab the slides. There are some resources there on how to make your sample set representative. You can also build your own data set, not just from what's going on, but you can make a data set look like how you want. You can start by figuring out what the constraints are. For instance, if you'd say, okay, I want to build a data set where all races are equally likely to get mortgages. And in that case, you just turn around and say, all right, we're going to build some kind of replace your dependent variable with some kind of function that generates a new output altered by those constraints. And if you're saying, well, now you're kind of tail wagging the dog, you are, but you're also making choices the same way that you're making choices when you just ride with historical data. There are a couple tools out there that will help you explore your data set and find bias. One of them is IBM's AI Fairness Toolkit, which is actually really cool. It will show you things with this data set like, okay, are there particular categories that are protected over another? So for instance, this is a actual analysis from the ProPublica risk assessment data set that we talked about in one of the early consequences for that, whether somebody should be released on bail. This is actually showing that there is a bias against men and towards women in that data set, that women are more likely to be given bail than men are. That's a bias in the data set. What you do with it at that point is kind of the choice that you have to make. Do you want to strip that out? Do you want to leave that in and deal with the consequences? There are different steps. There are also different steps that you can do things at. In this particular case, the IBM toolkit will allow you to do things like adversarial debiasing, which will attempt to actually put two different neural networks against each other and actually kind of make them fight to go, this one's trying to bias your data set and the other one learns not to do that, basically. Another tool that you can use is the what if tool, which is out there on GitHub. This is another way to show, okay, what are kind of the correlations between those two data? And what it will do is show you, here's a model, two predictors in this case. What are the differences between those two predictors? Why are two things, these two data points being, why are they predicted differently? And it will show you what things are what dependent variables or independent variables are weighted in that particular model. So there are different ways you can explore your data set and the outcomes and the predictors of those things to look for bias. But you have to have a good process in place in order to do that. You have to be willing to slow down and say, we need to take the time to do this right. Lastly, you have to know who can be affected in order to unbias. If your data set does not have, for instance, racial categories or racial classification inside of it, if your data set does not have gender inside of it, if your data set does not have trans people inside of it as even an option, you can't detect bias against those folks at that point. And even if you have them in there, you really need to know who can be affected by bias in order to unbias it. If there are particular zip codes that are biased for various reasons outside of the algorithm, like one's a Superfund site, et cetera, there's a bunch of toxic waste to this zip code, so people get mortgages really we don't give mortgages over there because we really don't want to buy people to buy stuff over there. That's an option or a consequence that can show up in your data set that can bias against those folks. Now, you can ask the question, do you want it to be? But that's the same question I'm asking you. You have to make a choice when you're building your algorithms, when you're building your models, that asks you, and I'm asking you to sit down and think about it for a little bit. Is this what you want to be in the world? So, moving on to class 3, the shade of overly simplistic maximization. Let's talk about pricing algorithms for a little bit, because this is fun, especially in the, global supply chain stuff that's going on. There were researchers that took 2 pricing algorithms. And if you didn't know, sorry to be the one to tell you, basically everything on Amazon is priced via robots these days. They took 2 common robots, 2 common pricing algorithms, and kind of put them in a sandbox with each other with a single product and told them to go find the maximum price. And then let them kind of train with each other for a while. And then what they did is they introduced a price change. They manually forced one of them to drop the price. Now, normally when you do this, when you see 2 things entering into a sandbox, you wind up at something called the Nash equilibrium. Without getting into the math of all of it, especially the economics of all of it, this is named after Thomas Nash, the guy who was the main character for Beautiful Mind. If these 2 things are competing fairly in the marketplace and operating under basic, the introductory assumptions that they had, they will wind up at the Nash equilibrium. If they're colluding with each other, they will actually wind up at kind of this maximum collusion equilibrium. So what they saw is that when you forced one of these agents, these pricing agents, to drop its price, you would expect this to happen. That one of them would drop and the other would kind of drop to the forced price because that was the actual equilibrium of price of this product. What actually happens is this. When forced to drop one, the other agent drops it in response, but then they start inching their way back up. When they're looking at each other and paying attention to what each other actually prices the product at, they wind up at a price that is not the Nash price. It's not the full collusive cooperative price, but it's definitely higher and back at what the average price was pre-shock. They wind up at this stasis. So I want to ask you a question. What if Amazon had built a salary tool instead? Instead of going to build something for recruiting, they said, well, build something that tells us how much we can pay these individuals, the minimum amount to pay these people, because we're a business and that's what we do. If they valued salary costs strictly and ignored all other factors, they could get, they'd hire a lot more women because they'd wind up being able to pay women 70 cents on the dollar. Now, that's obviously unethical and potentially illegal, depending on where you live. But it's possible. Machines don't understand ethics. They don't understand the world. I have a coworker who built, as a tool once, or as a part of a hackathon, a app that was called Foodies. And it was a food planning app because he just started a family. And when you start a family, you're, delirious with lack of sleep, and you have a bunch of things on your time, on your, asking for your time, including your job, your spouse, your kid, your house, etc. And so he was like, I'm just going to build a tool using neural networks to build for me a menu for the week. And he built it to prioritize a couple different things like cost, reheatability, whether he could reheat leftovers easily during the week, various macro level stuff, like in terms of protein, etc. He turned around and let it go. Now, there is a grocery store here where I live in Omaha, Nebraska called Hy-Vee. Hy-Vee, especially during the summer, runs these specials where you can get a chicken bratwurst for 97 cents. That's, less than the US dollar. And the algorithm kind of looks at that and says, all right, that's that. You can make a bunch of them at once and they'll reheat. It's high in protein. It's got the fats you want. Really cheap. Awesome. Problem solved. Bratwurst. Breakfast, lunch, and dinner the entire week. Bratwurst. It's funny, but it's also an amazing example of how myopic these tools can be, which leads us to class 4, the shadow of understanding. I added this one recently because of a tool that it was floating around the internet a couple months back. People were tweeting outcomes from it, and I had to include it in the talk. It's a tool called Delphi. Delphi is this tool that you can still go to. It's a research prototype designed to give ethical, moral judgments on a variety of everyday situations. And the internet did what the internet does with these kind of things, and immediately got it to be extremely racist and extremely sexist and just all around not great. So I was, had to play around with it. And it doesn't really understand things, right? What's happening when you ask it a question is that it is looking at its model. It's trying to build a NLP representation of those things and attempting to actually figure out the ethical correlation with those things. But what it's doing, the data that they have are these situations that they have harvested from Reddit. And now they're asking a bunch of people on Mechanical Turk, is this right or wrong? So they're really not doing a ton of legwork inside of the machine to really build some kind of ontology about ethics, etc. They're really just kind of going, well, do these words correlate kind of with yes or kind of with no? It's more complicated than that. But at its heart, you can tell from this question alone that it doesn't really understand words. And that's the trick. No AI understands words like you understand words. No AI is bringing a bunch of things to the table. And if you're worried about me using references to war crimes in this talk, I got some really good advice that it was perfectly okay to talk about murdering ham sandwiches in a conference talk. But to this point, like, if that's okay, I can also ask this, change this sentence slightly and go, am I allowed to slaughter a village of ham sandwiches if we have irreconcilable differences? And suddenly that's not, like, it's not clear if that's okay or not. It's pretty obvious that this tool is not anywhere close to being something that shows you the morality of a situation. They might as well have just put in a thing that says, here's the question. When they show you the question, they show you the percentage of people that said yes or no. And like that, you don't need AI for that at that point. The thing here is that humans are rarely single-minded. Okay? We rarely are focusing on a goal to the exclusion of everything else. And when we do that, it's usually catastrophic. We are surrounded by these things that cause us to behave in certain ways. The law, our boss, the other people that we care about, our individual goals. When we build a machine learning model, it doesn't have those baked into it. We can't get rid of those. When we're thinking through something, it's impossible to set those aside. If we don't build external consideration and information into the system about morality, subtleties, context, etc., these tools are not going to understand them. They can't. And it's really hard to turn those things into math, which is all they do understand. People are still working on this. And this is far from a solved problem. So this is an example of kind of that myopic viewpoint of how AI and machine learning work. This is a tool called a half cheetah, and it's a two-dimensional world, even though it's rendered 3D, that shows the opportunity for, or the goal is for this thing to learn to walk. And you can see what happens when it actually goes. It flips over and it just starts twitching its whole way. But the thing is that this is what the machine learning tool came out with. It said, this is the most effective way of travel. It's like, well, okay, yes, it is, given the parameters that have been fed into this tool. It's clearly not what oh, there it goes, right off the edge. It's clearly not what the researchers wanted. It's a failure case to them. But this is what machine learning is going to do when you just give it a goal that says, get as far as you can. It's going to do dumb things that you don't want, because you have to also tell it, get as far as you can while staying upright and kind of looking like a real animal, et cetera, et cetera, et cetera, et cetera. And that can get really tedious. So what can you do about that? Well, again, remember, models represent what was. They don't tell you what should be. You have to understand that, because that will help you say, all right, just because the thing told me to go get bratwurst, I don't have to go get bratwurst for every meal. Like, it's not your new AI overlord suddenly. Don't trust algorithms to make subtle or large multivariable judgments. Delphi is a perfect example of something I would never trust an AI to handle until there's rapid change in the industry. You can also try combining variables into composite variables and using those as your dependent variable. Instead of just having profit, build a convolution between profit and happiness and try and predict that instead. Now, there's a whole bunch of, we go, unpack the whole thing here about how you rate happiness, and et cetera. But that's potentially an option for you, is to try and use these composite variables. Last 5 is the simulation surprise. The simulation surprise happens when you are testing AI and machine learning in simulated environments. So here's an example. A bunch of researchers took a simulated robot arm and they were teaching it to basically pick up a box and move it. Or they were hoping it would learn that. Their fitness algorithm, what they were measuring it on, was how far did you move the box? So it got pretty good at picking up the box and moving it. Then they locked its grasper together, digitally. So it's not like it's not a physical robot, so you can't just rubber band it. But they stopped it in software from moving its little gripper. And they said, all right, now figure out how to move the box. And the robot said, well, okay, what I'm going to do is hit my gripper on the corner of this box, or the corner of the environment, rather. And that's going to force the gripper open. Because again, it's not physically bound. It's just a simulation, right? It's just like a video game. So the physics of the world is going to force the gripper open. And then I'm going to pick up the box and move it. Seems really smart, right? But it's obviously not what they were intending. And not necessarily what would happen in a real world scenario. Another example, there were researchers who were trying to use machine learning and computer vision to determine whether something was poisonous or not, to identify basically, is this a poisonous food or is this not a poisonous food? But when they generated and trained the data for these machine learning tools, they passed these in a predictable order so that it was always non-poisonous food and then poisonous food, non-poisonous food, poisonous food. What did the machine learning algorithm learn? That you pick every other one as the poisonous food because the simulation was that way. This is the simulation surprise, that there are things when we build a simulation of an environment, obviously it's less detailed than the real world. That's the point of a simulation. It's easier, it's cheaper, et cetera, right? But it isn't the real world. And there are things about that simulation and the simulated data that these tools will pick up on and learn that will not carry over into the real world if you try to use them. So what can you do about that? Well, first, you can be ready for it. If you build something in a simulated environment, if you're simulating training data, you have to be ready. You have to be sure that your data doesn't have patterns in it as much as you can. There's another example that came out from some of the, this was pre-COVID, but there was a hospital that was trying to train whether or not, or train a computer vision to figure out whether or not a patient had cancer based on whether or not they, based on their CAT scans. Problem was this hospital had 2 CAT scanners. One of them was in the normal portion of the hospital. The other was right near the acute ward so that they could get the acute patients, the patients in severe danger, et cetera, into the CAT scanner very quickly. And so there wasn't a wait for the other one. The CAT scans, the output, had text on it. The images had text at the bottom indicating which CAT scanner it came from. The machine learning algorithms learned that it was way more likely for the CAT scanner in the acute room or the acute ward to have a person who is cancerous than the actual other CAT scanner. It was a completely wasted example because they didn't scrub this identifiable, predictable data out of their data sets. You also need to learn not to confuse the map with the territory. Just because a simulation is behaving a certain way doesn't mean that reality is going to behave in the same way, right? You'd think that would be obvious, but you see people miss that all the time. Additionally, you do have to verify and check solutions derived from a simulation. They're not something you can just take and release into the real world for various obvious reasons. All right, let's move on to class 6, the apparition of fairness. Let's imagine we're going to go to Twitter and we're going to build something that does natural language parsing. Whether we're building some kind of sentiment analysis, we can tell, hey, a lot of people liked your tweet. All these quote tweets are positive as opposed to negative. It's identifying your ratio, basically. Those tools, or this tool that we're building, might work fine for normal language. But what happens with dialectical language? With, for instance, African-American English, with Southern slang, with any other dialect that happens to exist for English. How is that tool going to perform if our corpus only contains a whole bunch of normal standard English, quote unquote standard English? It's obviously not going to perform very well. But what's happening here, well, one of the reasons that happens rather, is that AI and machine learning tools are trained to minimize average loss. We talked about the correlation of 2 data sets before. In the case of machine learning, a lot of the times it determines how well am I doing by effectively measuring the distance between what you are saying it should be and what it actually outputs. And then it works to minimize those gaps using things like R squared or mean squared error, et cetera. Those are all tools that help you minimize the average loss. And that's a normal, fine way to evaluate data sets. You can, in our Twitter example, wind up with a data set that supports and works well for a large majority of people, but it doesn't necessarily work for a certain subset of folks or certain subsets of folks. This is called representation disparity. These systems can have a high overall accuracy, but low accuracy for these subsets of people who are not represented well in your sample space. Even if that data is in the sample space, these things can decide effectively, I'm anthropomorphizing, but what the algorithm will do is effectively diminish the input of these subsets and say, well, we're going to focus on broader accuracy. And this can be a problem if you want your tool to actually be egalitarian and you want it actually to be just. So what can you do about that? Well, you can consider your predictive accuracy as a resource to be allocated. Okay, you have a certain amount of predictive accuracy that will come out of a machine learning tool. You can decide how you want that to be allocated across different um, subsets of people, different subsets of the things in your data. There's a tool to do this. Hashimoto, Srivastava, Namkung, and Liang in 2018 came out with a paper that described what they called distributionally robust optimization. And that is a way to, it's instead a replacement for the mean squared error, replacement for that minimizing aggregated error. I recommend you go look at the paper. It's a great read. It'll get into the details of how this thing actually works, but it's a way for you to turn around and say, hey, I don't have to just try and solve maximum accuracy for as many people as I can. I can kind of parcel that out into things that I want. The last class we're going to talk about today is the feedback devil. So let's think about that for a second. Let's take that NLP we were working with, the one that doesn't work well for those dialect users. And we're going to build a product with it anyway. We're going to say, all right, it's fine. This is going to work for the vast majority of users. And that's what we want. What happens to the people who use those dialects? They're not really going to use our cool new product, are they? Because it doesn't work well for them. Well, okay. But if what we're doing is gathering the data from our users and feeding it back into our algorithm and retraining our algorithm and basically building a learning system that takes in new data, we're never going to get the data from those users. We're never going to get better at those subsets because they're not feeding their data into our system. We've now created a feedback loop. So let's talk about predictive policing, which is a thing that's been coming up more and more and more in the world. Predictive policing is this tool that allows police to effectively, it's an algorithm that basically predicts where crime is going to occur. So let's describe what would happen here. You have a neighborhood in city skylines, right? Average random city. This algorithm is going to turn around and say, all right, I'm picking this area for whatever reason based on my internal evaluation. This is going to be an area where crime will occur, right? I'm predicting crime will occur here. When that happens, the response is to send police there. All right, that's why they bought the algorithm, is so they can be there and be ready for this crime. When police are in an area, they tend to find crime. It's not necessarily that the crime is there or was increased. It's that they're finding crime because crime tends to happen a lot of places, whether minor or not. There's a lot of different laws, especially in the US, that you can fall afoul of without necessarily being aware of it. And when those, there are police there, so there are going to be arrests. When those arrests happen, they're recorded. And that means that crime in that area goes up, quote unquote. The crime statistics now have gone up in that particular area. So that means that the algorithm is going to go, crime is increasing here. We should continue adding police to this spot, to this neighborhood. This is now a feedback loop. If this predictive tool has raised expectations of crime in that neighborhood, police can be more aggressive there in making arrests because they're expecting crime. They're ready for crime. And in the end, what you can do is almost blight a neighborhood because the crime statistics will just continue to feed back upward. And the people who live there start moving out because the crime is now very high, even when nothing actually majorly criminal has happened. So what can you do about feedback? Well, this one's really, really difficult. And I have not seen anyone try to address this in a larger scale sense yet. You can ignore or adjust for algorithm suggested results. For instance, if you're building a shopping cart and you build like Amazon has, the people who bought this also bought this. Ignore when people click and say, I want to add that to my cart, because you don't want to build more correlation between those two. Because if you do that, you've created a feedback loop that now, yeah, more people buy these two together because you keep suggesting the two together. You can also try looking at control engineering instead of just looking at the actual feedback loop itself. Build tools into your feedback loop to control it. Like process engineering is this entire field of engineering that exists just to control feedback loops. And you have the option to turn around and use that to control your own feedback loops inside of your system. Which of the inputs do you want to value? Which of them do you not? All right, bring this thing home. In summary, for class 1, the phantoms of false correlation. You know what questions you're asking and trust the conditional probability over straight correlation. For class 2, the specter of biased sample data. Recognize that data is biased even at rest and make sure your sample set is crafted properly. Excise those problematic predictors, but beware those shadow columns. Build a learning system that incorporates false negatives and false positives as you find them. Try using adversarial techniques to detect bias. For class 3, remember that models tell you what was, not what should be. Try combining dependent columns and predicting that, and try complex algorithms that allow more flexible reinforcement. Class 5, don't confuse the map with that territory, and always reality check solutions from your simulations. Class 6, consider predictive accuracy as a resource to be allocated and possibly seek external auditing of your results, or at least another team evaluating it. For class 7, ignore or adjust for those algorithm-suggested results and look to control engineering for potential answers. So all of this can sound hard and overwhelming. What can you do right now? Well, the first thing, kind of what I talked about at the beginning, take time to think about what it is you're solving. What question are you solving? Who are you solving it for? Whose data do you have? And how was that data made? What biases could it contain? Think about those questions. Turn around and remember that models represent what was, they don't tell you what should be, okay? You can also hire data scientists. They will help take your stuff to a new level. They understand a lot of the things about how to avoid a lot of the biasing of data sets when you're doing sampling, et cetera, about how to actually make sure you have representative data sets in the first place. Or you can get training on that yourself. There's boot camps, Coursera, Udemy, actual universities offering courses on things. There are a ton of different places at this point you can get data science learning as a base, as a complete background or bottom to actually build your machine learning skill set on. You can also try finding others trying to solve the same problems. There are places like the AI Now Institute, the Georgetown Law Center on Privacy and Technology. Knight Foundation has an AI ethics initiative. There's a website called Fast AI that has a lot of really interesting content. And places like the Algorithmic Justice League, working to apply justice bake justice into algorithms. Find and abide by some set of ethics guidelines as you're doing data science. Things that ask questions like, what is the privacy of the data that you have? Have the people who've given you their data given consent to use it in that way? Are you being transparent about the use of that data? Are you being transparent about the algorithms built on that data? And who owns the data? Is it you? Is it your customer? Who owns the resulting outcome, the resulting model and algorithm? Is it you? Not to be a corporate shill, but Accenture actually has a really good page on this, a really good pamphlet on how to actually set up some universal data ethics. I found this actually really fascinating. And it can be a really good baseline for how to go build your own set of data ethics and adhere to it at your company. Like once you've done it, hold yourself to it. Otherwise, you did a bunch of work for nothing, right? All right. Thank you very much for coming to listen to my talk. I really appreciate it. Like I said, the resources are at that bit.ly link. You can download the slides. There's my Twitter. My name's Arthur Dohler, and thank you very much for listening.